When considering work and energy, a very important concept is conservative forces. We know work is done by forces. But what do we mean by a conservative force? Very important to understand this. Okay. So energy is conserved, but this idea of a conservative force means that it's a force that does work on an object which is then stored as potential energy. So it's not so difficult in concept, but what does this mean? Well, when only conservative forces are involved on an object, you have conservation of what's called mechanical energy. I just use the symbol cap E for that. Now, mechanical energy is what we're usually interested in our everyday lives, to run an automobile and to operate electric motors and the output work that they do, etc. So mechanical energy, it's a combination of kinetic and potential. And so it could be any combination of those. The key thing is that it's wrapped up in both and it doesn't convert to some other form. So if the forces that are acting on conservative, then the sum of the potential and kinetic equals, if it doesn't change, it's constant. That's the key thing. So it can convert from one to the other. If you drop a ball, it starts with mostly potential energy, and as it falls, it converts to kinetic, but the total amount stays constant. So there's no loss of usable energy. In other words, typically, energy converts to heat. Eventually, I should say, it converts to heat in most practical situations. And heat, once it converts to that, it can't be converted back to its original form. All right, so the idea of non-conservative forces. If a force is non-conservative, then the mechanical energy, the kinetic and potential, changes. So then instead of writing that the mechanical energy is K plus U, we have to add another term. So what we're adding here is this WO, which means work other. Work other. Work done by another force that's not conservative. All right. It can be an applied force like a rocket engine on a ship. That would be plus. However, typically, it's a force that restricts motion, for instance, and is negative. Or it could be zero, in which case there's just none at all. So I'm making a point now in the end to say that this work other is often done by friction. And that's a force that would typically slow something down and convert the kinetic energy into something other than potential. And it would be negative work, usually converted to heat, converting energy to heat. Now, having given you an idea what conservative forces are all about, let's consider gravitational potential energy. Symbol U sub G, standard. So we're going to consider a falling mass. So here we have a ball of height h, and it has mass m, and mg, of course, is the gravitational force acting on it. We start with a potential energy, UG1, at the top, and it falls down along some path. Notice I chose a random path, and there's a reason for that. This is the final potential energy of ball 2. Well, I should say the second one, for our purposes, the final position. And basically, the height is the distance from which the ball falls, and so the potential energy is simply that height times the force of gravity acting on it. Okay, so you might recognize that that's also equal to the work required to move it from here all the way back up to its original position. Force times distance. So that's the potential energy, mgh. So that's nice. No real tricks there at all. Now, as the mass falls from position 1 to position 2, what happens to UG? That's right, it goes down. So the change going from one position to the next, it's getting less, so it's negative, right? Negative change. But what kind of work does gravity do? Gravity's doing work on this ball as its potential energy decreases. And the kind of work it does is all dependent upon the relative directions of the force of gravity and the displacement. Well, they're both in the same direction. They're both down. Therefore, work done by gravity is positive. The force is in the same direction as the displacement. So that tells you right away that work done by gravity is not equal to the change in potential energy. Work done by gravity as the ball moves from here down to here is not the change. Because the change is negative, but the work done by gravity is positive. So work done by gravity is negative change in gravitational potential energy. So that's, remember, a change is final minus initial. So in this case, it'd be final position minus initial position. But the negative of that would be the initial position minus the final position. So that's why it's UG1 minus UG2. Now, as the ball falls, if we ignore air friction, for instance, and any other forces that might be acting on them, and that's realistic, because there really isn't anything of import, then from the work energy theorem, we have that the total work done is delta K, and that's just work done by gravity, because gravity is the only force acting on it. So that's negative delta U sub G. So, summary of all this, mechanical energy is K plus U sub G. So as this thing falls, the kinetic plus the particular potential energy it has at that moment comprise the entire mechanical energy. So the change in the kinetic added to the change in potential, so as it's falling, kinetic goes up, potential energy goes down, those are equal and opposite. And as long as that's the only force acting on the ball, namely gravitational force, those changes are zero. Now, to solve problems using this concept, we have the following scenario. If you expand this idea, K2 minus K1 plus UG2 minus UG1, we get the following. We can put the ones on one side, namely identify all the kinetic and potential at position 1. And that equals all the kinetic and potential at position 2, which equals all the kinetic and potential at position 3, etc. So, there's your formula, and you could expand that to any number of positions. Now, the reference position does not matter for the value of the change. In other words, here's the ball. Whatever height h is, if it drops, say, 3 meters down to the bottom, if that's what the difference between these are, that's fine. There's a certain change. If instead we started here and dropped it 3 meters down, that change would be the same amount, assuming the floor isn't in the way. So the changes in potential energy are independent of the reference position. However, the actual values of the potential energy could be different. So let's take the floor and bring it all the way down here. So if we drop this from here to here, or start here and drop it from here 3 meters down, then that change is the same. But the value of potential energy from here and here is different than the original, height h that we started with down to here. Those values of potential energy are different, the changes are not. So UG1 and UG2, it does matter where you are, but not the change. And the path also doesn't matter. So if I took this path, this randomized path versus a straight path, the change in gravitational potential energy and the work done by gravity is still the same. Basically, like if you're going sideways, gravity doesn't do any work. It suspends its desire to do work. Well, not desire, but the actual doing of the work is suspended momentarily until it starts going down again. Then it goes up a little bit, and there's some negative work done by gravity. But when you add it all up, ends up being the exact same thing. It's path independent. Gravity is a conservative force, and those characteristics just described are characteristics of all conservative forces. So if you're taking notes on this, let's just summarize what we have here in this situation with a falling ball. We have a gravitational force as a conservative force because the work done on the ball on the way down is positive. Positive work, force and displacement in the same direction. Now that increases the kinetic energy, but that's a change in K, positive in this case, representing an equal and opposite change in the amount of gravitational potential energy. Thus, it is lost. It's negative. If you push or throw the ball back up to the original position, that would result in a loss in the K. If you throw it from the bottom, it slows down until it gets to the top. However, as it's slowing down, there's a gain in gravitational potential energy. Now, work done by friction is energy lost in the form of heat, so usually you don't want it, unless you're trying to heat the house like I'm doing right now with the wood stove, but usually you want the mechanical energy. And heat represents a reduction in the mechanical energy. Does all this make sense? I'm sure you would say yes. Certainly you would. It's so clear. You do believe, right? Other, well, remember, work other is like friction, so we don't want any of that. Now, let me revise and simplify the brusdom from the last video. If you ever find yourself flinging dead fish off of a pier into a lake, make sure you let go.